time and frequency dissemination using software-defined radio. On the one hand, it's an opportunity to share a little bit some of the ongoing projects, including with our friends from the observatory, Besançon and Paris Observatory, and also try maybe to trigger some interest in using what we're implementing, because developing new experiments is one thing, but having people use them would be even better. So I'd like to share a bit with you some of the latest results on the white rabbit time dissemination and some of the wired and wireless time and frequency dissemination that's been developed in the lab. So just as a quick reminder for those of you that I've been repeating this for most of the latest conferences, but just to try to remind everyone what is time and frequency. We're used to having frequency as inverse of time, but when you're disseminating time and frequency, there are actually two orthogonal quantities, and there is actually no relation between accuracy in time transfer or frequency transfer. If you think of it, frequency is a narrowband quantity, meaning that you just consider a sine wave. What is characteristic of a frequency transfer is a pure sine wave, which has no time characterization. Every period of your sine wave will look similar to the neighbor. So you have no timing capability in terms of time transfer, in terms of frequency transfer. On the other hand, time transfer is an intrinsically broadband topic where you wish to have as high accuracy as you can on the timing of a signal that is exchanged between the two speakers. And so that's why you see that these two quantities are actually completely unrelated. You can have a broadband signal that will accurately transfer time, and then you can try to recover some sort of carrier information, you can try to recover frequency information, and one does not preclude the other. So when you want to do time transfer, frequency transfer is easy enough. You just send a carrier, and this carrier, when you look at the comparison between this remote carrier with your local oscillator, you compare this with a mixer, and you've got the frequency offset that you try to correct either on your own oscillator or you observe the difference. So that's easy enough. A bit more challenging is time transfer, because time transfer being a broadband measurement, you need some way from one hand of spreading the spectrum, and on the other hand of timing with highest accuracy, and yet not losing too much of a signal-to-noise ratio related with this broadband signal transfer, where you're spreading the energy over this broadband. So if I take inspiration from radar, because actually when you're doing radar time of flight to a target, that's exactly what you're doing. You want to measure the time of flight to a moving target with the highest possible accuracy. This means when you're doing radar measurement, you try to spread the spectrum and measure the time of flight to a target. So the most stupid way of spreading the spectrum is to taking a pulse. A pulse, a Fourier transform of a pulse, is a constant function. So you spread the spectrum over the inverse of the duration of the pulse. Technologically, it's kind of difficult to make a strong pulse. And furthermore, it's kind of stupid because you don't have a duration over which you can do a convolution to try to lower the noise. If you just think of it, averaging, when you take 1/n sum of the samples, the sum of the samples is the averaging that decreases the noise level by square root of n, the number of samples. And if you take a pulse is just a few samples, so you're not going to have any averaging capabilities. Your signal-to-noise ratio improvement is going to be very weak. On the other hand, what you can do is to broaden the spectrum by just sweeping the local oscillator. So if you sweep the local oscillator over bandwidth B, then taking the inverse Fourier transform of the return signal will give you the time domain transfer function, so the impulse response. That's what frequency step continuous wave radar are doing, FSCW radar. And finally, what you can do in what is, for example, done in GPS is to spread the spectrum by running a pseudo-random sequence. What's important is that this pseudo-random sequence has to be known. If you know the pseudo-random sequence, then you benefit both from the duration of the pseudo-random sequence, so the time it takes to run the sequence over which you can average, and on the other hand, because you've got this chip rate at which the transferred information is changing, you spread the spectrum through the pseudo-random sequence. And so this brings you to this quality factor, which is the pulse compression ratio. PCR is this quality of service information that tells you that pulse compression ratio is the duration of your message times the bandwidth. And so the duration is in seconds, the bandwidth is in hertz. So in other words, this is a unitless quantity that gives you the improvement in terms of signal-to-noise ratio. The correlation width, so the cross-correlation width, will be inverse of the bandwidth, 1 over b, and the pulse, the signal-to-noise ratio will be improved as T times b, the pulse compression ratio. If you think of this in the digital domain, if you take a digital information that is switching at b bits per second, and you do this for duration t, then t times b is simply the number of bits in your pseudo-random sequence. So actually, the pulse compression ratio is equal to 10 log of n, the number of bits, and the longer the sequence you send, the better your averaging capability, so the better your capability of extracting signals from noise. Now, if you look at some of these time transfer software or implementation, you will very often see a lot of Fourier transform. And the first time we had a look at the software for decoding GPS, for example, we were struggling understanding why correlations were implemented with so many Fourier transform. And the reason for this is that if you remember your convolution theorem, the convolution theorem tells you that convolution of x and y is the Fourier transform of x times the Fourier transform of y. And since correlation and convolution are closely related, just the time is flipped, the correlation between x and y is Fourier transform is the Fourier transform of x, and you flip time by taking the complex conjugate, so that's Fourier transform complex conjugate of y. So whenever you want to efficiently implement a correlation, you run this in the Fourier domain, especially for large sample number. So if I just show you this using GNU Radio Companion, so the open source software for prototyping discrete time signal processing, you see here that I take a noise source, and what's important is that this noise source is a known sequence which I assume to have a local copy of, and then I can have 2 time delays. That would be in radar signal 2 targets, and these 2 targets are returning. So on your receiving antenna, you've got the vector sum of the electric field, and what you want is to detect these 2 time delays from your 2 targets. So actually, if you want to correlate your reference signal with the return signal from the 2 targets, you take the Fourier transform of the reference signal, multiply conjugate with the pattern that you received, and actually taking Fourier transform or inverse Fourier transform is just a matter of putting the minus in the minus omega t on the direct or the reverse, and this is a matter of standard. So actually you can take reverse Fourier transform on both operations here and take on the spectrum analyzer the direct Fourier transform. And just to illustrate how correlation is linear, if I take the same delay for both targets, they overlap. If I move one target, you've got one correlation going away. If I move the other target in the other direction, you've got the target in the other direction. So you see here that the linearity of correlation allows you to recover as many delays as you've introduced on your reference signal. It allows you to detect as many targets as you want on your return signal. So having reminded you of these basics that I'm going to use throughout the presentation, I'll try to illustrate 3 applications of time and frequency transfer. The first one is over the radio frequency spectrum, and that's a topic that we were asked to look at by our industrial partner in the joint laboratory, FAST Lab. And Gorgie Timing wanted us to have a look at whether we could use one of these Internet of Things, the trendy LoRa protocol for time and frequency transfer. I'll show you the reason for investigating LoRa a bit later. The second one I'm going to illustrate is two-way satellite time and frequency transfer, which is a software-defined radio implementation of a SATRE radio modem. And the last illustration will be wired over the optical fiber network white rabbit time and frequency transfer and its use. So the first application I would like to show you is using the LoRa network. So what is LoRa? LoRa is one of these proprietary protocol that is being promoted at the moment for this trendy Internet of Things massive network sensors. And Semtech is trying to promote this technology, which on the one hand is a narrowband communication, which allows long-range communication, and it's low bandwidth. LoRa means long range. And it's a low bandwidth communication under the assumption that if you want to send a few bits, like a temperature or presence or absence or location, you don't need high bandwidth communication. And this is actually how they achieve several tens of kilometer communication range with only a few tens of, we have actually only 10 milliwatt transfer. So what Semtech has done is they decided to use a chirp spread spectrum communication technique, where you have here the waterfall over time and frequency display. So that was a record that we did using a software-defined radio receiver as a LoRa transmitter was communicating. Here you've got the frequency. This is centered on 868. That's an industrial, scientific, and medical band, ISM band. And over the 868 megahertz band, you see one of these communications where over time you've got this chirp, you've got down chirp and up chirp. And the basic principle is that you will have some frequency jumps in these up and down chirp, and the frequency jump actually encodes the bit state of a LoRa communication. Now, this is a proprietary protocol. It's not documented, and actually the very few documentation that you're going to find in the patent are wrong. Probably they did on purpose. There is a nice analysis of the patent by Semtech showing how they try to mislead you by patenting erroneous protocol. And actually, we are not going to look into the cryptographic encrypted message here. We just focus on the header. This header is actually the same header whenever you're sending a message from what they call, so what you would usually call a server, they call a gateway, and what you usually call a client, they call an endpoint. So endpoint would be this low-cost sensor that you distribute massively, and the gateway are the data collector. They try to send the data to a network server. This is this whole Internet of Things idea. And so whenever you start communicating between a gateway and a client, actually all communication is initiated by an endpoint, a client, which tries to get information to the gateway. You get these 8 chirps, and these chirps are always the same. So if you know the shape of a chirp, you can actually correlate with this known sequence. That's exactly what we did with FSCW in frequency step continuous wave. You know that you have some sort of spreading of a spectrum over a given bandwidth. And here we know the slope and the frequency excursion of a chirp, so we can do the correlation. And you get here these 8 correlation peaks that allow you to time the signal. Now, in the LoRa protocol, these chirps can be 125, 250, or 500 kilohertz wide, which tells you already that we're going to only have very poor timing capability because 125 kilohertz is inverse of 8 microseconds. So even if you have oversampling with improvement on the time resolution equal to the signal-to-noise ratio, let's say you have an SNR of about 100, well, at best, you're going to get something like 100 nanosecond time resolution, which is not great, but okay, let's try to see what we can do with 100 nanoseconds. And the other information is that they got this spreading factor. This spreading factor is actually the duration of each chirp. So each chirp can be elongated, what they call spreading factor from 7 to 12. And every time you increase the spreading factor, you double the duration. So if you double the duration, you double the integration duration. And we saw earlier that your PCR is B times T. So if you have the same bandwidth, increasing the time will allow you to increase your pulse compression ratio and your signal-to-noise ratio by doing this. So the idea is, can we use one endpoint that would be synchronize a hydrogen maser, whatever time reference you want, and synchronize multiple receiver, multiple endpoints on this system. So what we're doing is, so this was initiated by Didier Doncez and his colleagues at Grenoble, who are trying to promote LoRa for Orange and Semtech. And they're computer scientists, so they know the computer science level. And as our activity is more towards the radio frequency level, our interest here is to look at the OSI layer 0, so that's the hardware layer. And what we want to look at is there's nothing you can do on the computer science protocol, because once your message has been sent, you know that your timing capability is, even if you have a real-time operating system, there's always some latency, there is always some uncontrolled latency in your communication protocol at the higher OSI layers. So similar inspiration to what we're doing with White Rabbit, we look at the hardware layer, and what we send is one endpoint initiates a communication towards a gateway, And this communication times some sort of duration delta t. Remember, speed of light, 300 meters per microsecond. We aim at something like 100 nanosecond time resolution. So whenever your two LoRa endpoints and gateway are located at more than 30 meters apart, then this time of flight is going to be significant. So we want to measure this time of flight, so both endpoint and gateway are monitoring the radio frequency spectrum. The endpoint initiates a communication, the gateway receives this communication, and both these endpoint and gateway are measuring using the radio frequency software-defined radio receiver. This RTL-SDR is one of these radio frequency receiver. You split part of the energy from the antenna that is going to the LoRa receiver, and this fraction of energy that is routed towards the receiver here will allow you to timestamp the endpoint transmission and the gateway reception. And because this is the same message that you're timestamping on the endpoint and the gateway, you can actually deduce delta t from the second transmission here, that is the return signal from the gateway to the endpoint. So if you have this ping-pong message between gateway and endpoint, you can have twice delta t. I will not get into the equations, but it's kind of obvious that if you have T1, T2, T3, and T4, then you can get delta t by subtracting these two quantities. And because this T3 timestamp has been measured when the message was transmitted, actually the timestamp here has to be transmitted in the second message from gateway to endpoint, which kind of breaks the architecture of LoRa, because LoRa assumes that when you initiate a communication from endpoint, the gateway is allowed to answer once but not twice. So you have to trick a little bit LoRa to do this. So that's the basic architecture. So we have a gateway. The gateway is the reference. So in this case, you have a 10 megahertz reference that clocks your radio frequency receiver over here. So you assume that this receiver is clocked by the hydrogen maser. You've got a 1 PPS signal, which gives you the time, which is actually fed by capacitively coupling one of the baseband signal from the radio frequency receiver. And these two quantities are streamed to the single board computer, the Raspberry Pi. So the important aspect is that the A to D converter is both clocked by this reference signal and sampling the 1 PPS signal. And the only thing that you know in the timing information here is the timestamp that has been introduced by the A to D converter. Everything above that, USB processing is asynchronous, but you don't care because everything has been timestamped by the A to D converter, including the radio frequency signal that has been coupled from the LoRa receiver to the RTL-SDR. The architecture is the same on the endpoint, the one that you want to control on the gateway, except that this time, this 10 megahertz oscillator is the one that you want to control. And this time, again, we distribute the 10 megahertz on the RTL-SDR. You just need to multiply to 28.8. That's the frequency that this guy expects you to give you. The FPGA is creating the 1 PPS by counting the 10 megahertz reference. And again, we have the exact same architecture, except that this time we control the frequency source, so there's a feedback loop that tries to control the 10 megahertz on this signal. So that's the inspiration actually was given from this GNU Radio conference presentation, where this author is using LoRa to do some ranging experiments. So to make a long story short, this is what Mohammad has been working on for the last six months. And that's what you get in terms of time domain analysis of frequency evolution and island deviation. So as usually with this kind of control, what you see is that your free running oscillator is is an accurate frequency on the short term. And actually this was overnight when the lab, the window was open. So that's when the lab is cooling due to the drop of temperature. And you see that you've got something like a 15 hertz drift of a local oscillator. Now, because we only have a very poor measurement of the frequency that is measured by LoRa, we only have 125 kilohertz bandwidth and pulse durations of a few tens of milliseconds, we're unable, using the direct counter, to measure accurately the frequency. So on the short term, we only have a couple of hertz resolution on the frequency, but because here the gateway was clocked by the hydrogen maser, on the long term, you do have a stabilization exactly like you would have with a very low frequency DCF77 or whatever long-term stabilization you have. And so what you get is on the short term here, you've got the stability of your local oscillator. On the long term, you've got the stabilization of the hydrogen maser. And of course, at the intersection of the two Allen deviation is the time constant of the feedback loop. So here, the feedback loop was controlled every 3 minutes, which is obviously far too often. And that should be in a couple of hour time constant. So the reason why we were interested in this LoRa control is that Didier Doncez and his colleagues have launched one of these nanosatellites that is fitted with a LoRa transmitter in a polar orbit, 550 kilometer altitude. And their idea was that actually you could make a poor man's GPS system by using some of these low Earth orbiting satellites, transmitting some sort of frequency reference over the Earth using the LoRa control. So in the idea of Didier, it was just a one-way time transfer similar to NTP. Now the light will take 4 milliseconds to go from the satellite to ground. So of course, that's kind of an inaccurate time transfer. Well, maybe that's enough for your application. And in this case, what we're looking at is whether we can control using two-way communication with the satellite to remove this uncertainty on the time of flight of the LoRa signal from ground to the satellite. So that's one example of a two-way time transfer. I'm not really sure we're going to continue because the chances of reaching reasonable accuracy are quite weak with this narrowband signal. But just to give you a hint about the workflow that we're following when we're addressing this kind of challenge. The second story I would like to share with you is the two-way satellite time transfer. That's the story that we initiated with our colleague from Observatory in Paris and in Besançon. So you might be familiar, so that's the two-way distribution room. So that's the two sequel to my presentation. Now I would like to discuss satellite time transfer, and afterwards I'm going to discuss White Rabbit time transfer. So two-way satellite time and frequency transfer was initiated in the 1980s, I believe 1983, for a first paper by a German author from Stuttgart who implemented, well, actually, if you look at the papers from 83, and Andreas Bauer has been very helpful in identifying these original papers, you see that the Mitrex modem was implemented, and the author refers to GPS as a pseudo-random sequence that is transmitted over radio frequency waves, and by correlating the signal, we're going to recover the time. And the very early tests were initiated prior to the sale of the SATRE modem by TimeTech, also a German company. And basically, whether you're looking at Mitrex or SATRE, you don't find any public information. The fact is that there is no publication on how they work. You take a black box, and hopefully you pray that it works as expected. Well, not completely. If you go in the very early papers, you will find some of the information from the original paper 1983, where you are told that the pseudo-random sequence that acts like a noise is a 14-bit sequence, which is 16,000 bit long, which is truncated to 10,000 to make it easier to do decimal operations. So if you just think of it, okay, we have a 14-bit pseudo-random sequence, the natural approach would be to say, let's try to look at linear feedback shift registers. Now, the beauty of reverse engineering the SATRE protocol is that there's only 756 possible maximum length pseudo-random sequence generator, which are 14-bit long. So actually, we can take a brute force approach and just try all the possible codes on the SATRE received signal. And then we're told that they are 10,000 bit long out of a 16,000. So when do you actually start? Well, you might say, let's start with all zeros. But all zeros is a forbidden state, because all zero, when you XOR 0 and 0, that gives you a 0. So if at some point you have all zeros in your register, it will just keep on staying 0, which is not a pseudo-random sequence. So let's take the other solution, and let's start with all ones. So we assume that in the beginning, the register is filled with all ones, and we just run the pseudo-random sequence generator, 14-bit long, and we keep the first 10,000 bits. Now, at the moment, the data rate is 2.5 megabit per second, so that gives you the spreading of your spectrum, and inverse of the spreading gives you the time resolution improved by the signal-to-noise ratio. This is important because a 10,000 bit long 2.5 megabit per second repeats every 4 milliseconds. I'll tell you why that's a problem for me. So we take all the possible codes. We've seen earlier that taking a Fourier transform is done efficiently for correlating. So in MATLAB, you do this as a matrix operation that goes quite fast. And then we take the inverse Fourier transform to display the correlation peaks. And when you do this, so this is a record from our colleagues from Besançon Observatory that gave us access to the SATRE receiver. So you record using software-defined radio the 70 megahertz IF bandwidth, IF frequency, and because it's BPSK modulation, exactly like you're doing with GPS, your signal S of t is composed of an offset, a frequency offset between your receiver and the transmitted signal, plus phi, the phase that holds the pseudo-random sequence. And what is very well known is that if you square this sequence, then your phi, which is equal to 0 or pi, it's a BPSK, binary phase shift keying, so your phase can take two states, 0 or pi. When you square the signal, 2 times 0 or pi is 0 modulo 2 pi, which means that you collapse the spectrum and you're only left with the carrier frequency at twice the frequency offset. And because you've collapsed all the energy in the carrier, what was below the terminal noise now rises over the terminal noise by about 20 dB, and you can identify the stations, and for each one of the stations, so each one of these sequence here is a station that is transmitting from a European observatory, and you can just correct for the frequency offset, so you remove half of 2 delta omega that you have here, and you correlate because we know the chip rate, we know the sequence, so you just run the correlation. And we've got 756 possible codes, so that's from 0 to 755. These are all the possible codes. And for each station, you see, well, actually, you see that these 756 codes are not so orthogonal to each other. You see that some of them are you've got multiple solutions. So here we have, for this station, 2 possible codes. We have here another 2 possible codes. So these 14-bit sequences are not so orthogonal to each other, but because the authors have only selected 32 out of the 756 codes, if you trust that they did their job wisely, and that's what I find amazing about metrology, where people don't publish anything, you don't know what the codes are. But in the paper you find, well, just trust me, I selected the right code. Okay, so they selected 32 of these 756 codes, and you trust them that somewhat they are as orthogonal as possible. So from this analysis, we can identify which LFSR match each station, and we can try to recover the SATRE information. So, do we actually trust the SATRE modem? Well, it happens that some of the open source, no, not open source, some of the source code for decoding SATRE has been leaked, and we do actually know what the codes are. So what you might say is, let's try to analyze the orthogonality of the codes. So this is GPS. Well, GPS, the gold codes are only 1023 bit long, and remember your pulse compression ratio is B times T. So if you shrink tenfold the duration of the code, well, your orthogonality is going to be decreased. So your gold code exhibits some sort of 10 dB orthogonality, so that's minus 10 dB with respect to the same code, which is, of course, correlation is 1. If you look at the SATRE modem, well, you've got a few points here which are not so good. And actually, you identify a bug, and 2 of the codes are the same. When you tell this, people tell you, yeah, we know, and we just don't use them. So, okay. So just don't use the bugs in your SATRE modem. And my idea was, what about replacing the 1980s SATRE code with the current GPS L5? L5 is 12,230 bit long, so about the same length. And how does GPS behave? So if we take the GPS L5 codes from this website and we zoom onto the color code, well, what you see actually is that SATRE is not too bad, but you could improve by using L5. So that's L5 complex. GPS L5 is a complex code because you can use Bok modulation. So you've got I and Q component. And you can actually say, I only keep the I components of a real part. And if you look actually at these quantitatively at this color scale, you see that SATRE is about minus 11 dB. So the side lobes of your correlation peaks are minus 11 dB. And if you were to take L5 complex, you gain 2.7 dB, and with the real part, you gain 3 dB. So there is definitely a benefit in running the L5 real part of the code as opposed to the SATRE pseudo-random sequence that were selected in the 80s. So that's the story about SATRE. From there, what we did, the actual experiment is we connected a software-defined radio on a derivative of a parabola dish going in the two-way time transfer room. We added a bit of amplification. We observe the offset, the frequency offset at twice delta omega. We remove the frequency offset and we correlate the pseudo-random sequence. And from that, we can identify the sampling frequency offset. And because the A to D converter is clocked by the metrological source, you know that whatever frequency offset you find on the A to D converter is a frequency offset between the received signal and your local reference. Remember, the beauty of correlation is that correlation is a linear operation, so that if you get the cross correlation between X, your local copy, and the received signal, which is the remote copy, phase shifted, then the correlation actually exhibits the same phase shift. So whatever phase has been introduced by the remote speaker is actually found on the correlation that you get. So here is an example of the measurement. This is the signal that is transmitted by our local modem in Besançon. There's the received signal, which is the sum of all the signal received from all the other observatory. And by taking the cross correlation with the code, you can identify the time difference between the two messages. To give you a long story short, over a 4-second analysis, we are able to measure, thanks to a high signal-to-noise ratio, the time difference with about 13 nanosecond difference, and that would lead to about 2 nanosecond time difference over 3-minute record. So that's what it actually looks like. When you look at all the received signal, you can find the codes of all the European observatories and the frequency offset. And actually you realize that all the frequency offsets are a bit off with respect to their official value. And that's actually a frequency difference between the expected frequency and the real frequency of the satellite sending the signal back to Earth. So the satellite is a bit off with respect to its nominal frequency. But you can actually find all the European observatories, and then you can timestamp the Besançon time with respect to the remote observatories using post-processing of a recorded signal. So that's actually what it looks like when you do a ranging experiment. So this is where Besançon is transmitting a signal towards the satellite. The satellite returns all the signal received from all the observatories, including Besançon. And so if you autocorrelate the signal, you get the time of flight between what you sent and what you received. And that's the two-way trip between the transmitted signal and the received signal. And what you actually see is that the two correlation peaks are separated by about 264 milliseconds. That's because at the beginning of each second, the correlation sequence is offset by 200 nanoseconds, and that allows you to have an absolute time. And that's important. Remember, I told you earlier that the codes repeat every 4 milliseconds. And you cannot do absolute ranging if you have a pulse repetition interval, the PRI in radar, which is 4 milliseconds. You have an uncertainty of 4 milliseconds, except that at the beginning of each sequence, you get a time offset that allows you to timestamp absolute time of 200 nanosecond offset, and that gives you the time of flight two-way trip. And if you do a bit of geometry, Besançon, we're located at 47 degrees north, 6 degrees west. The satellite is 6 degrees east. The satellite is located 37 degrees west. So if you do a bit of trigonometry, you actually find that the 264 milliseconds matches the 40,000 kilometer distance between the ground station and the satellite. And from the screenshot that was provided by Eric, we actually find here that the two-way time of flight is 262 milliseconds. Remember, that's 264 plus or minus 2, the uncertainty of the PRI. So that matches what the SATRE modem is detecting. So the question is, okay, you can do ranging, and you need to know the location of a station on the surface of the Earth to identify this absolute time. How can you do if you don't input the location of the observatory on the both ends to get the absolute time? I don't have the answer. To the best of my knowledge, you need to introduce the location of the observatory if you want to get this answer. So this is what you get actually from the analysis. You detect the cross-correlation peaks, which repeat every 4 milliseconds. You do a linear fit on the phase of the correlation peaks. That gives you a fine frequency offset. And once you've removed the fine frequency offset, of course, a linear phase is a frequency. And you're left, if you take, that's your BPSK, that's your binary phase shift keying message, and the payload is actually the time information, so the second of the year that is transmitted over the air. So this gives you, again, the same information, except that this time, this is not a ranging information. This is a comparison, time comparison between Paris Observatory and Besançon. So these are two received signals. This was transmitted by Paris. This was sent and received by Besançon. And here you see that the time offset is, of course, less than 4 milliseconds. The two observatories are aligned. And again, I have no idea how you can solve this without the 4 millisecond uncertainty, which is solved by the ranging of each station of both ends. So that's the final story about what happens when you forget to clock on the hydrogen maser. That was just to highlight the need to clock on this is using the internal oscillator, so the poor quality TCXO from the software-defined radio. You see here that your phase is drifting. Actually, it's completely off in this case here. This is when clocking with the hydrogen maser, and you see that your phases are stable as you're recording. So just to highlight the need to clock the A to D converter with a high stability clock. If you run it on the TCXO, the phase is going to rotate too quickly and you will not be able to recover the information. So basically, we know how to recover SATRE information, and our work in the project is to make an emitter. Now, the first step will be to try to make the same emitter that you can find on the SATRE using the BPSK modulation. But SATRE was developed, or Mitrex was developed in the 80s. Now it's 2022. So you can imagine that over 40 years, people have developed a bit of expertise in digital communication. And that's actually the kind of information I would like to bring into this field, thanks to the help of my colleague Hervé Beuglen at XLIM in Poitiers. He's an expert on digital communication. And what we're looking at is how can we optimize spectral efficiency. Spectral efficiency is simply the fact that the satellite channel supplier gives you a given analog bandwidth, and we need to put as many bits per second as we can in this analog bandwidth. So if you just take the stupid BPSK modulation, well, the only thing you can send in BPSK, so here is your constellation modulation that generates BPSK. That's your channel modeler where you put noise and frequency offset, and that's your channel decoder. So if you run a BPSK, your satellite transmits a signal, you receive the signal. This is the analog spectral occupation. And what you see here is that on the constellation, so real part and imaginary part of the IQ, you just get 2 dots. So that's very inefficient because you've got only 2 states, 0 or 1. Of course, the beauty of this when you're doing satellite communication with low signal-to-noise ratio is that if you increase the noise level, well, your point cloud is going to spread, but still you can separate 0 and 1 and have hardly any overlap until you put so much noise that you will no longer be able to separate the two clouds, and you get bit error rates associated with the overlap between the 2 clouds. So the question is, what is going to be the impact of putting more bits per timestamp? And so if you generalize the story, you've got BPSK, 1 bit per time step, but you can do QPSK, 2 bits, and then you can do what people are doing with digital video broadcast. Whenever you're watching TV, you actually have this kind of modulation, where you have QAM, where you have both amplitude and modulation. And so the fun thing with software-defined radio is, so you duplicate your blocks, you run this with BPSK, QPSK, and QAM, and surely enough, you get your correlation peaks. So you run the pseudo-random sequence, you modulate it at BPSK, QPSK, or QAM, and you get your correlation peaks that repeat with a pulse repetition interval. That's your analog spectrum, and these are your constellations. So you've got BPSK, QPSK, and QAM. And if you increase the noise level on your channel, well, that's where you see that actually the higher modulation schemes on BPSK, you still got some separate clouds. I don't know what happened here. On the QPSK, the clouds start merging, and on QAM, you just have 1 big cloud. You cannot separate the bits anymore. So you see that your trade-off is between signal-to-noise ratio, where you can accept a bit of noise as long as you can separate the various point clouds, and the number of bits that you can squeeze in the channel, in the analog channel. Now, people are transmitting TV from satellites, and that's 8 megahertz bandwidth from 36,000 kilometers away. So I don't see why we would be limited to a BPSK as in the 80s and not be using some of the QPSK, QAM modulation. So that's basically a little bit the approach. Let's try to see if we can take 2022 modulation schemes and bring them to the hardware of 1980s that is still being used for time transfer. Work in progress. Whenever you record 3 minutes of SATRE modem, you're generating about 7 gigabytes worth of data. We're sampling complex quantity from 2 channels at 5 megasample per second. And my computer just kind of load 2 times 7 gigabytes and process them. So at the moment, we're splitting this file and trying to process the file piece by piece and trying to see how we can improve this communication scheme. So the first step will be running on an FPGA the classical Go code from GPS L1 just to show that it can be done. Japanese guy have done this, Taiwanese guy have done this. We need to get up to date in our project. And this is work in progress. You can find it on the OSCIM Digital GitHub if you want to have a look at this. And the next step, once we get this working by the end of the year, is to go for some of the more fancy QPSK or QAM modulation and trying to maybe increase the duration, because you see here that if you take all the observatories, Paris, Besançon, PTB is down there, Braunschweig, the NPL, National Physics Laboratory, or INRIM, you see that they're all at the same 260-something milliseconds. But if you take PTB, they're already 4 milliseconds off. And how do you make the difference between 262 and 266 milliseconds? I asked Andreas, he didn't answer about this part, but to my best of my knowledge, you have to introduce somewhere some knowledge about the location of the observatory. And if you look here, if you want to go from northwest Finland to southwest Spain, so the whole extension of Europe, you've got more than 29 millisecond difference. And I don't know how you solve this in absolute duration. So that's ongoing work on software-defined radio implementation of two-way satellite time transfer. And finally, maybe we can learn a little bit about what people have been developing lately, digital audio broadcast, DVB-S, so that's digital video broadcast over satellite, where people are using the OFDM communication. And most interestingly, what they introduced is the cyclic prefix, where periodically you insert this known pattern separated by the data. And the beauty of having this known pattern separated periodically in the data stream, if you look at this tutorial on the DAB decoding, is that if you autocorrelate this guy with this guy, and if there is a slight frequency offset, then your phase is going to rotate from here to here, but the autocorrelation will only give you the frequency offset times the duration, which is the phase offset between these two guys. And you can very efficiently identify the frequency offset by using the autocorrelation. So this is very well known for DAB and OFDM communication. And again, this is knowledge that is not used in two-way time and satellite frequency transfer, and I think it would be worthwhile introducing. So here is an example of decoding DAB. You've got a coarse time information, that's a drop of energy whenever you have a purple arrow, that's a coarse time information. And from this coarse time information, you know where this cyclic prefix is located. By taking the autocorrelation of the cyclic prefix, you get the frequency offset, you correct the fine frequency offset, and when you do again the correlation after correcting the fine frequency offset, you get this beautiful correlation peak that allows you to have a fine timing information. So everyone doing modern digital communication needs to solve the issue of time and frequency synchronization. And we're not using this knowledge in two-way time and satellite frequency transfer. So that's really a loss of expertise. So I think there is something to be learned from all these digital communication schemes. And 5G is going to be much worse because 5G is time-synchronized network. So all these protocols that are being developed for 5G, not only we can contribute by giving or providing high-stability oscillators, but I think we can learn from these people by using their modulation schemes and processing techniques. So that concludes what I wanted to tell about two-way satellite time and frequency transfer. And for the last few minutes, for the last 15 minutes that I have left, I'd just like to share with you what we're doing with White Rabbit. And especially I would like to highlight that in the time dissemination room, there is this 18-port switch that is only waiting for users to connect if you want to have the hydrogen maser or the cesium clock from the observatory shared with you. You see that there is only one port that is being used at the moment in Pip's room, and there's another 17 slots waiting for you to connect to the White Rabbit network. Now, one of the limitations, in my opinion, of using White Rabbit is that it gives you two very stupid information. White Rabbit will give you 1 PPS, 1 pulse per second time information, plus or minus 60 picosecond, and it will give you a copy of a 10 megahertz. And personally, I don't care about 10 megahertz. I don't care about 1 PPS. There's no use for 1 PPS and 10 megahertz. The question is, how do I make use of this 1 PPS and 10 megahertz for my practical application? My application, as I'm going to show you, is distributed radar. Maybe your application is AOM modulation or whatever, A to D conversion, distributed A to D measurement. Whatever your application, most probably it's not going to be 10 megahertz and 1 PPS. And so I've been searching for a while for how to use this 10 megahertz and 1 PPS until I ended up finding on the Analog Devices forum a description of the AD94 40-something chip. So this AD9548 is actually 12 years old, and only now I've realized that we can use it for time and frequency dissemination. And actually 48 is obsolete by now. They have released the AD95 46 and 45, that Analog Device, you lower the number, but it's a newer chip. And the AD95 48, 46 and 45 are actually even much better. And so what I'll try to show you is by coupling White Rabbit with these network distribution, with network clock distribution chips, you can do beautiful things, I believe. So the first thing is, what is my application? My application that I tried to show, but I'm not really sure anyone has looked at this. This is this presentation I recorded for INSA Lyon last December, if you want to have a look at a detailed presentation of the distributed radar application. So just as a quick reminder, 30 kilometers from Besançon, in Haute-Saône, there is the GRAV radar emitter. So GRAV is the space surveillance radar, the French space surveillance radar that will illuminate any spy satellite flying over France. And it's a bistatic radar with the emitter located in Haute-Saône next to Besançon and the receiver located on Plateau d'Albion, south of France. So it's a bistatic radar extending the whole length of France. And GRAV radar is a continuous wave radar, because if you're looking at satellite, just knowing the velocity of a satellite and knowing Kepler's law is enough to identify the orbital parameters. So if you just want to know when a spy satellite is going to fly over France again, you just need to know its velocity, and from multiple measurements you will identify its orbit, and that's enough to know where the satellite is on its orbit. So what we're looking at is we're illuminating the satellite or whatever from ground, and the satellite is going to introduce, remember that the Doppler shift for a radar system is 2 times F over V over C, because you illuminate the target and you get the signal back, so that's 2 times the carrier frequency, velocity of the target divided by the speed of light. And this continuous wave source, I would like to add to the velocity information the direction of arrival. And if you want to have direction of arrival on a continuous wave system, you need to have multiple antennas. So if you want to have multiple antennas that are spatially separated and you want to synchronize them, you need something like White Rabbit. And because we're 143 megahertz, that's 8 nanosecond period. So if you want to have something like 3-degree angular resolution, you need about 60 picosecond timing accuracy, which is exactly what White Rabbit is giving you. So let's do this. Let's try to synchronize multiple receivers. So that's what we did here. We have the White Rabbit receivers. We have the software-defined radio receivers over here, 4-channel receiver. And in this experiment, we're just doing some aliasing on purpose. So GRAV is at 143 megahertz. These software-defined radio receivers are sampling at 200 megahertz, so that's a Nyquist frequency of 100 megahertz. And if you take the alias at 57 megahertz, you get the GRAV signal by aliasing to baseband. All these software-defined receivers are clocked on the White Rabbit network. This one is connected to observatory. This one is connected to the local copy of White Rabbit. So there's about 2-kilometer optical fibers between these two guys, and they are simulating the distributed radar architecture over here. Beauty of software-defined radio, when you want to put 4-channel, you just make 1 channel, and then you copy-paste, and you get a 4-channel receiver. So that's a nice thing about software-defined radio. You don't buy a new hardware, you just copy-paste your processing blocks. Again, to highlight the need for high stability oscillators, these two software-defined radio are clocked on a hydrogen maser. This is clocked on the TCXO, and this is about 5 minutes duration. You see why you need a high stability oscillator. Here, you would be hard-pressed to identify the speed. So that's your Doppler shift over here. This is the direct wave from grav. This is positive frequency, so that's a plane coming towards you. That's a plane outgoing. And here you can easily have the speed of the plane from the Doppler shift. Here you need to compensate for the fluctuation of a local oscillator as you are detecting the planes as a Doppler shift as the planes are flying overhead. So when you do this, also you need some sort of good quality amplifier. That's just to highlight the difference between a power amplifier and a low noise amplifier. So here you've got the traces of the planes. Of course, with a power amplifier, which are not low phase noise amplifier, you just hide the received signal below the phase noise. So here's a plane flying a few kilometers from Besançon, and this is what you detect over here. And as this plane has been turning along its path, you see here that the plane has turned, and that's the projection of the velocity vector towards your antenna array. So obviously you detect the speed of the plane flying overhead. So if you do this also with fighter planes will have an obvious signature. This is commercial flight with a nice linear path which looks as an arctangent as you project the velocity. Fighter jets are just turning everyone around, and you see speeds above 360 hertz. 360 hertz would be 900 kilometers per hour for a commercial flight. So that allows you to easily identify fighter jets over commercial flights. So usually you don't use aliasing. You want to use frequency transposition from a radio frequency band to baseband, and that means that in a usual architecture of a receiver, you would like to have a local oscillator at the frequency that you want to operate at, in my case 143 megahertz, and you want the sampling system, so the clocking the A to D converter, to be both synchronized on whatever reference you're using. So actually the White Rabbit will need to be used for two applications. One of them is generating the radio frequency signal that clocks the local oscillator for frequency transposition of a radio frequency band to baseband, and the second one is synchronizing the acquisition on the A to D converter. And so that's the objective of my use of the AD9458, is to try to generate these two signals. And furthermore, I would like to do this on an OEM single board computer because I don't want to spend like 5,000 euro on each node of the distributed radar system. So can we try to deploy White Rabbit in such an environment running on a Raspberry 4, a Raspberry Pi 4, which obviously means that we need some sort of modern Linux. You cannot use one of these outdated Linux, which is what CERN is using at the moment. So CERN is promoting their White Rabbit system for their 3.10 Linux, which is from 2014. And of course, a 2014 kernel, Linux kernel, will not support the Raspberry Pi. So that's been our effort with Gwen, trying to upgrade White Rabbit to run on modern Linux, trying to get it to run on ARM CPU as the ones fitted on the Raspberry Pi, and trying to get actually White Rabbit to work, because you're going to see that White Rabbit works in a very limited condition and not in ours. So what does it look like to generate the radio frequency signals? If I just go back, the first part is how do you generate this radio frequency signal? And this is the architecture of using the AD9448. The AD9448 takes two inputs. It's a system clock and the reference input. And the way I found to use this AD9448 to generate anything between 0 and 450 megahertz, and that's actually found in the application note from one of the early application notes from Analog Device, is that you feed your reference clock, your radio frequency clock, as the system clock, and you feed the 1 PPS as the ref in. And because this AD9448 can have as low a bandwidth of 0.01 hertz, so that's 10 millihertz, well, that will nicely discipline whatever output, whatever radio frequency output you're generating from this chip on the 1 PPS input. And so by doing this, you can generate on any link of your White Rabbit, on any node of your White Rabbit network, anything that is phase and frequency synchronized between 0 and 450 megahertz. And that meets my requirement of distributed local oscillator for transposing grav to baseband. So if you look at what it looks like, this is my 143 megahertz. You see here the date. This was November 16. This is November 17. I kept the persistence of the oscilloscope for 1 day. And you see that over 1 day, the two 143 megahertz separated by 2 kilometers of optical fiber have neither drifted nor have they shifted with respect to the reference 1 PPS. So this proves that over 1 day, there has been no phase jump and no frequency drift because the persistence has kept these two signals overlaid, whether we're taking the local node or the remote node. Nevertheless, what you do see on looking at the phase noise is that White Rabbit, each experiment was duplicated. This is why there's two curves. This is a local distribution, so you take the 1 PPS, split it, you take the 10 megahertz, split it locally, you get this kind of phase noise, and if you distribute over White Rabbit, you see that you have something like a 10 dB degradation of your phase noise. So it's well known that the local oscillator or White Rabbit are not very good. They could be improved. It's been done at SATRE in Paris. So the local oscillator of White Rabbit would deserve some improvement, but still you see that we achieve the objective of phase and frequency synchronizing over the White Rabbit network here at 143 megahertz. So now that we have a local oscillator, you want to sample, you want to acquire the data synchronously over the White Rabbit network. So what we did is we bought some of these PCI boards that implement White Rabbit, and when you buy these boards, well, you want them to run on whatever hardware you have, and we want to run this on the Raspberry Pi. CERN is working with this outdated 3.10 kernel. They say it's fine for CERN, good for them, but the 3.10 kernel is not supporting the Raspberry Pi. So last summer, Gwen with Matisse have spent a significant amount of time upgrading the drivers from 3.10 to 5.12, which is the current kernel, and now White Rabbit is working on ARM CPU with some of the latest kernels. So once we had White Rabbit working on the Raspberry Pi, we wanted to be able to collect data. So you buy some of these A to D conversion boards that fit on the FMC carrier here, and you run data acquisition, and you expect all your samples to be aligned. Well, not at all. All the samples, I'll skip the software defined, all the samples, so what Matisse did, he collected data over the network where we had 10 megahertz distributed over two boards separated by 2 kilometers, data sampling at 100 megasample per second, so we have 10 samples per period, and you expect the phase to be the same on any point of your node. And if you look at the phase distribution, you get something that is distributed. So I asked Ravier, why is your White Rabbit not synchronized? And Ravier tells me, well, at CERN, we're happy with 10 nanoseconds. That's enough for us. But that's not enough for me. I want to measure 143 megahertz, 8 nanosecond period. I cannot measure with 10 nanosecond uncertainty. And so the conclusion is they put two oscillators, one for White Rabbit, one for the A to D converter, and these two oscillators are not synchronized. This one is free running. So you start the acquisition at a known timestamp, but your A to D converter is just running its own rate. It's not White Rabbit synchronized. So what we're struggling now with is trying to synchronize the A to D converter on the White Rabbit network, and this is what we did. Gwen is working on implementing the digital PLL in the FPGA. I did it my way because I don't understand FPGA, so I did it with the AD9458. And what you see here is Gwen outputs the White Rabbit internal clock, which is 62 megahertz, 62.5. From this reference clock and the 1 PPS, I can drive the AD9458 to generate the 100 megahertz that will clock the A to D board, and I clock the A to D converter not by its internal clock, but by this synchronized clock. Again, this is the local White Rabbit, this is the remote White Rabbit, and now if I trigger A to D conversion on these two boards, you see here over 40,000 seconds, that's about 10 hours measurement, the phase has shifted by less than 0.1, actually 0.01 radian. And if you look at the time deviation of this result, well, you start with a 60 picosecond at 4 seconds, so that's about a few 10 to the minus 11, and you decay as 1 over tau, so that's actually your white rabbit time deviation. So basically, we did achieve synchronization, except at the moment it's done using external hardware, and Gwen is working on putting this digital PLL inside the FPGA so that we have a phase-synchronized acquisition over the white rabbit network. And with that, I conclude my presentation summarizing what we did. So we tried to investigate LoRa communication for time and frequency dissemination. We've seen that LoRa is a narrowband protocol, only 8 microsecond time accuracy. So you don't expect to have high resolution, but maybe that's enough if you want to do something like replacing DCF77 or TDF. We've seen how you can use the low-level hardware protocol to identify time of flight and frequency. We tried to expand this knowledge to two-way satellite time and frequency transfer and upgrade the knowledge on this communication protocol by using modern digital communication techniques over the protocol that were implemented in the 80s. We've been upgrading White Rabbit to run on modern Linux, ARM CPU, QEMU x86. So now we've got something that is a bit up to date. And we completed synchronization of the A to D converter on the external clocks. If you're interested in this, this is all uploaded on the OSKIM Digital GitHub repository. You can get White Rabbit on the latest kernel and working with Raspberry Pi. You've got all the tools over here for running on Buildroot and work in progress, trying to discipline the A to D converter of the White Rabbit clock and streaming data over the dark fibers of White Rabbit, not only to transfer time, but also to transfer low-rate digital streams. And with that, I thank you for your attention.